Alright guys, so I know I'm a little bit behind on this, but I did want to give you a short video about the sum of independent random variables and just kind of go through a couple of different ideas here. Alright, so the first idea that I want to make sure to go through is just the basic idea is we're still talking about discrete random variables. So if we have discrete random variable x and discrete random variable y, now those could be geometric or negative binomial or some other type of independent discrete random variable that we haven't talked about yet. Okay, so as long as they're discrete random variables, okay, I'm going to write that down just so that you can't accuse me of lying to you later. So as long as these are discrete random variables, okay, and x has PGF of g of t, okay, and then y also has its PGF of g y of t, okay, then if I decide to add these two discrete random variables together, and you did some of this, remember how you had to make the table and you had to figure out what happened when you added x and y together, and you got each of those values in your table, and then you had to work out the probabilities, right? So what we're going to say is this is a theorem, and it's actually proven inside your Hayes-Harris textbook on page 61. I'm not going to go through that proof, but I am going to go through a couple of other examples, okay? But we will say that x plus y will mean that the new PGF will be equal to gxt times gyt. All right, now this is significant because this means, remember, we could do things with the PGF. We could find expected values, we could find variances. And so now when I combine discrete random variables, I can now get the PGF of that combined random variable, and therefore I can get their expected value and I can get their variance based off of the processes that we learned last night. Okay, so the first one I want to talk through is just a simple example. Okay, I want us to consider a binomial expansion. Okay, n and p. This is very general. All right, we're going to say that n is all positive integers, so a very large system here, and of course the probability p is between 1 and 0. Okay, now what I want us to do is I want us to find the PGF for x. Alright, so that's what we're going to be doing over the next couple of minutes. Alright, so in order to do this, what I want you to do is I want you to recognize that a binomial expansion is just a Bernoulli, right, that has been repeated over and over and over again. So if we say that a specific Bernoulli, okay, now remember Bernoulli would then be defined as y Bernoulli, sorry, I shouldn't have that there, Bernoulli, and then the number of trials would be 1 and the probability would be p. So if I have this, then that means that x is the first Bernoulli plus the second Bernoulli. It's just a combination of all the Bernoullis all the way up to n Bernoullis, right? So it could be as many Bernoullis as I want, because that's all a binomial is a Bernoulli that's been repeated over and over and over again. Now we can put this together because we can get the PGF of a Bernoulli, right? PGF of Bernoulli, you're going to do 1 minus p times t to the 0 power, right? Because that's probability of getting 0 successes. And then we're going to have p times t to the first power, right? And hopefully you're comfortable with that. If not, go back and look at the PGF stuff. When we put all this together, we should get 1 minus P plus PT, just like that. Okay? Now, if this is the case, then if I'm going to find Gx of t, should just be Gx of t. So now I want the PGF of the binomial. Remember, that's just the combination of adding all of these y's together. And if each y is 1 minus p plus pt, then that would be 1 minus t plus pt to the n power, to show that I have n numbers of y1 plus y2 plus y3. And this is using this idea up here of when I add two variables together, then I just multiply their PGFs. And so therefore I have my final answer, which is that the PGF of a binomial is 1 minus p plus pt all to the n power. All right, so let's go ahead and look at the next question I got for you, because I do have. All right, so let's look through one more example. This one is with a discrete uniform variable. All right, we've got values 1, 2, 3, 4, 5, and 6. And then we've also got a discrete uniform variable 4, which is a tetrahedral die, a four-sided die with values 1, 2, 3, 4. So essentially 2 dice, right? It wants us to use the method of PGFs to find the probability distribution of x plus y. All right, so we'll go ahead and start with that. We will go ahead and write out each of the PGFs. Okay, you may remember that g of t for a discrete uniform is t over n times t to the n minus 1 over t minus 1. Okay, if you don't remember that, don't worry too much about it. It's very likely that on an IB question that part A will actually be show that the PGF of a discrete uniform variable is blah blah, and so you'll be given that. Yes, you'll need to use all the stuff that we learned in the previous couple of lessons to be able to get that, but I think you're hopefully getting comfortable with that PGF stuff by now. All right, so we'll go ahead and move on with this. Just we'll say that's given to us. Okay, so I'm going to have Gxt, so x was the 6-sided die, so that would be t over 6 times t to the 6 minus 1 over t minus 1. And then I'll have gy of t, the PGF of y, which similarly will be t over 4 times t to the 4th power minus 1 over t minus 1, just like that. Now, a couple of things that we want to recognize is we do need to put these together eventually. Okay, so what I would like for us to do is recognize that this, remember, right here, where did this come from? Well, remember it came from a PGF where I had 1 over 6 times t plus t squared plus t to the cubed plus t to the 4th plus t to the 5th plus t to the 6th, right? Go back and remind yourself of that if you can't remember why. But remember, this was just a geometric series of things from 1 to 6 where they'd been added together. 1 6t, 1 6t squared, 1 6t cubed, right? So hopefully you'll remember that. If not, go back and look at the video where I show how to get the PGF of a discrete uniform variable, and you'll see this. Okay. Likewise, we want to do the same thing for the gy here, which will end up being 1 over 4 times t plus t squared plus t cubed plus t to the 4th power. So now we're going to do exactly what we learned in the previous video, which is to get the PGF of x plus y, what I need to do is multiply this times this. Right? It's the g of x times the g of y, right? The PGF of x and the PGF of y, and we're going to multiply those two together. So if I do that, I'm going to have 1 6 times 1 4th, which would be 1 over 24. Now I need to make sure to distribute all these t's. So if I multiply t by t, there's only one way I can get t squared. I can get t cubed by doing t and t squared, or this t and that t squared. Those are the only two ways to get t to the cube. Then I'll be able to get t times t cubed, t squared times t squared, and t times this t cubed, and so I'll have 3 ways of getting t to the 4th. From then on, I'm going to have 4 ways of getting t to the 5th, t to the 6th, t to the 7th, and let's see, even t to the 7, no, by t to the 8th, I can only get 3 of them, right? Because oops, sorry, that's not what I meant to write. I was definitely thinking 3. So 3t to the 8th, because I'll have the t times the t cubed times t to the 5th, t squared times t to the 6th, and then t 4th times t to the 4th. So I'll have 3 ways of getting t to the 8th, 2 ways of getting t to the 9th, and 1 way of getting t to the 10th. Now, hopefully you'll recognize this as being a PGF that's coming from the possibility of x being, x plus y being anything from 2 to 10. So we could actually create our table now, right? And say, well, my random variables are x plus y. And what values can they have? Well, they can be 2, 3, 4, 5, 6, 7, 8, 9, or 10, right? And we can do that by looking just at the 2 sets of dice, right? I could get anything from 2 all the way up to 6 plus 4, which is 10. And so now I want the probability of each of those. And remember, the PGF is just the probability times t to that power. So that would be 1 over 24 times t squared. So that's 1 over 24. The next one should be 2 over 24. The next one will be 3 over 24. Okay, then so on and so forth. Got a couple of 4 over 24s there. 3 of them to be exact, then back to 3 over 24, 2 over 24, and 1 over 24. Yeah, those are all 24s. Okay, awesome. So we can actually double check that, right? Because if it is a probability distribution, they should add up together to give us 1. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 4 is 14, 18, 21, 22, 23, 24, 24 over 24. Yes, it checks out to be a probability distribution function. Woo! And guess what? We ain't even done yet, my friends. We ain't even done yet, because the next question wants us to find the expected value of x plus y. So how do I get the expected value? Well, now that I have the PGF, that's a piece of cake. Remember how you had to do that before? That was a lot of work that you had to do before in order to be able to get this. Now you don't have to. That's one of the reasons why we made you do all that work before, was to recognize when we can use the PGF that it's actually not all that bad. So the first thing I need to do is get g prime, x plus y of t. And so of course that is the derivative of this function right here, which is just 1 over 24 times 2t plus 6t squared plus 12t to the third plus 20t to the fourth plus 24t to the fifth. Yeah, it's a lot of writing, but it's all right. You may, even as you're kind of working through this, you may recognize why it actually works. But I'm going to leave that to you. All right. Now I need to do g prime of x plus y of 1, because that should give me the expected value. So go ahead, put 1 in for all of those t's. And when we add those things together, 2 plus 6 plus 12 plus 20 plus 24 plus 28 plus 24 plus 18 plus 10, it should end up giving us 144 divided by 24 and give us an expected value of 6. Go ahead, please check that out. Make sure that that's correct. but that should be our expected value right there. All right. Next, it wants us to find the variance. And of course, to get the variance, we're going to need the second derivative. So we'll go ahead and find the second derivative. X plus y of t. Still 1 over 24. Now it's just going to be 2 plus 12t plus 36t squared. You should be able to do all these derivatives by now, right? This shouldn't be a big issue. Wow, 120. This is stretching my brain a little bit now. 6 times 8 would be 48, 4, 12, 6, 168. Hopefully I'm getting all these right. 7 times 4 is 8, 2, 14, 15, 16, t to the 6th, 6, plus 144, t to the 7th, plus 90. That one I'm pretty sure I got right. T to the 8th. All right, so just double check, make sure I got all those numbers right. I'm pretty sure I did. Punch them in your calculator, whatever you need to do, make sure you get those numbers right. And then, of course, we need g double prime x plus y of 1. So we work that out, punch in a calculator, and we should get 34.167. No, I didn't do that in my head. I did it on my calculator, just like you should. So go ahead, do it in your calculator. Make sure you get 34.167. Okay, now of course that is rounded, so I'm going to put an approximation there. All right, now we can get our final variance here, because the variance of x is equal, sorry, this is x plus y is equal to, remember our formula from last time, g double prime of 1 minus g prime of 1 minus g prime of 1 squared. Go ahead, put those numbers in. You should be able to take the g double prime of 1, slam it in here. You should be able to take the g prime, slam it into both there and there. Remember to square it before you subtract it. And hopefully when we do all that, we get a final answer of a variance of 4.17. Woo! That is slamma-jammin'. But it is kind of neat how it works. It's also neat that it is less work than we used to have to do. Anytime we can do less work, we're not really going to complain about that, are we? Awesome. So the last question says, check your answers to B using the formulae for the mean and variance of a discrete uniform distribution. So we're going to go ahead and move up to the top to try to finish this question off. So remember that a discrete uniform distribution, the expected value of x, this is not in your formula packet, but again, this is one of those things that they would probably have you work out ahead of time. You really don't need to memorize it. But the expected value of a discrete uniform is you take the number of terms, you add 1 and then divide by 2, which in the case of the first one would be, if n is 6, that would be 3.5. And the expected value of y then would be 4 plus 1 over 2, so 2.5. Okay. Then we will do the variance, which is very similar. So the variance of x is going to be x squared minus 1 over 12, and you can go back and look at your notes if you don't remember that. Sorry, that's not an x, that's an n. Okay, we work that out, put the 6 in, and we should get about 35 over 12, because that would be 6 squared, 36 minus 1. Then we've got the variance of y, which is equal to, this time, 4 squared minus 1 over 12 still. And we should then get 15 over 12. Alright, that's an equal sign, not a negative. Alright, so with that, we should be able to do just the expected value of x plus y is equal to the expected value of x plus the expected value of y. And that's something you did back in section A, which in this case, yes, it works because 3.5 plus 2.5, yes, is 6. Check that one off. And then we need to do the variance. So I guess I should have done that in green. Now I'm going to do the variance down here. So remember, variance of x plus y is equal to what? See if you can remind yourself. It's just the variance of x plus the variance of y. So we're going to take 35 over 12 plus 15 over 12. And we should get 30, 40, 50 over 12. And 50 over 12, my friends, is approximately equal to 4.17. So it works. So there you go. We learned how to use PGFs to deal with adding independent random variables. Okay, that's what we did on the whole first part over here. Hopefully you don't have something with as messy a derivative as this one, but you know, it happens. And then over on the other side, we worked and just made sure that connected with and worked with the other things that we've done before back in section A when we learned about expectation algebra and variance and things like that. All right, so that's the end of my video. Thanks for watching.